So, good afternoon, everybody. I will continue today on the lecture about chapter 1. And as I mentioned in the previous class, it's better if you already get the textbook already and you read the chapters in advance. And I have already uploaded all the slides to the course website with the content of each chapter that we're gonna follow through the semester. And in the lectures and the slides, you're going to see material that's not in the textbook, and some portions of the textbook are not covered on the slides. So whatever the portion of the textbook that's not covered in the slides, like a section or something, that's because we're not going to cover that in the course, and I'm not going to require you to study for any exam. But I will be clear about that throughout the whole semester for each specific chapter, right? But chapter 1, you should read the whole thing. Everything is included, and these next few chapters as well, okay? So I will just share my screen here now. So just make it clear that all the lectures that appear here, lecture chapter 1, lecture chapter 10, and so on, they are all available. And as I asked you in the previous class, if any of these links that you click here has a problem, doesn't go to a specific page, just let me know, I can correct the issue. I also uploaded the first lecture to my YouTube channel. And what I usually do, I download it from Zoom to my computer, and I just make some adjustments in the audio to don't be so bad. And then afterwards I upload to YouTube, and that takes a little while. So that's why I'm able to upload it to YouTube by the end of the day of the class, right? So that's why it's not so automatic. I don't know why exactly, but the first lecture here from last Tuesday, my video doesn't appear until minute 2. So before here, you just see this blank screen, but my voice is there. But then afterwards, you can see the screen on the side. And the idea is to be something like this, that you see these slides or whatever I'm showing here, my screen on the left, and then my video on the top. I always have some little issues with the technology here. And for those at home, I cannot see the chat in my screen whenever I try to put it here, but then when I maximize the slides, it usually disappears. So you can just unmute yourself and say something, and it'll be able to answer. And when you talk, everybody in the classroom here in person can hear you as well. Another thing, I sent an email about the classroom. Everybody knows it's going to be here on 112. And the other thing is that someone did that group me link, and the student shared it in the chat, and I saw it at the end of the class. So I sent an email with that. If you did not receive my emails, I'm putting all these emails as announcements on Canvas. So that's going to be the practice. All emails that I send to you, I'm going to just also save them as announcements on the Canvas website. Okay? Any questions? Let's go. Oh, yeah, so right now I can see the chat. So that varies every day. If you want to ask a question from home, you can also use the chat. At least at this point, I can see it. In the previous class, we discussed the syllabus. I went through the syllabus and the structure of the course. And I also gave you some basic definition of what is demography and what's going to be covered in this course. And now we're going to continue on these other topics here. And for example, this subtopic, variables and observations, of course, coronavirus pandemic, demographic models, Lexis diagram, ratios, rates, and probabilities. All this material here, it's not in the textbook, right? So you have to both read the textbook, but then also watch the lectures and or read the slides to see everything that was covered in the classroom, okay? Let's see here the slide that we are at. So now I'm going to just talk about this major demographic equation that it's pretty much a really simple equation that provides us information of how we expect the population size of a specific society to be in the following year, in a specific year, based on information on fertility, mortality, and migration from the previous year. And human population either increases or decreases. So we see changes in population size due to pretty much the three components in demography, the three processes in demography: fertility, mortality, and migration. And there are two ways for someone to enter society: either being born or someone moving into a specific society, moving into a specific country, moving to a specific state, for example. So here when we are talking being born, we are talking about fertility. And here we are talking about people moving into that specific area, that specific location, which can be a county, a city, a state, a country, and so on. And there are two ways of leaving a specific population: either by dying, so that's mortality, or someone moving out of that specific society, someone emigrating, getting out of that country, that location. So population can only change by way of a limited countable number of events. It's really complex for us to do population projections to kind of try to see how the population is going to be in the future. There are specific agencies that do this very well, and also several demographers. And I mentioned to you the UN has projections that are available for free in their website. The Census Bureau has as well, and several other agencies. But it's possible to do these projections. It's not so simple. But actually, when we are doing population projections, we have to take into account these three things: fertility, people being born; mortality, people dying; and migration, people moving in and moving out from a specific society. And how do you just summarize all this information in an equation? That's what is shown here on this slide. So here we have, for example, the population in time t. Let's say that's the population in January 1st, 2020. And here is the number of births that happened between January 1st, 2020 until the beginning of the next year, t plus 1. So in this case, it would be number of people who were born in the whole year of 2020. How many people died in that specific year at the beginning of 2020 until the beginning of the next year, but without counting the next year? The number of deaths. The number of deaths that you experience in a specific year in that population will decrease the size of that population. The number of births will increase the size of that population. So we add births and we subtract deaths. The number of people entering a specific population, the number of migrants entering that population, is symbolized here by I. So people entering that population from the beginning of the period until the end, so t to t plus 1. It will add to that population. And the I can symbolize two different things. It can be both international migration or internal migration. If we are talking, for example, about the population in the US as a whole, the I is going to be capturing only people entering the US from other countries. So it's only international migration. And the correct term for that are immigrants. We are trying to count how many immigrants are entering the US, right? And if we are trying to understand the change in population size in the state of Texas, in the state of Texas, people can move from other countries to the state of Texas. So we are also talking about immigrants, but we can have people moving, in my example here, throughout the year of 2020 into Texas from other states in the US. So those would be internal migrants to the state of Texas, and the correct term for them is immigrants. So the correct term for people entering a country from another country, immigrants. Entering a specific area from another area within the same country is internal migration, immigrants, okay? And a specific area can also lose population by having people moving out from there. If I'm talking about the US, I'm talking about international migration, people moving to other countries outside of the US, of course. And the correct term for that, for those people, would be immigrants. And if we are talking about the population of Texas, people can move to other countries. Again, international migration, immigrants. But these people from Texas could be moving to other states within the US. That's internal migration. And the correct term for that is out migrants. So these terms here are just important, and we're going to talk again about that. I'm going to just come back to them again in the chapter about migration, both internal and international migration. But it's important to emphasize that people who move to another place, another residence, and the standard of the Census Bureau, people who move to at least another county are already considered migrants. Even if they move from one county within Texas to another county in Texas, from Brazos County to Harris County, for example, those people are migrants. They are internal migrants. From the point of view of Brazos County, someone getting out of here is an out migrant from Brazos to Harris. If I live in Harris, those people are in migrants from Brazos to Harris. Okay, so that's just the point of view there. But overall, we can estimate the population at the beginning of the period in the next year by using the population at the beginning of the period in the previous year, add the number of births that happened throughout the previous year, subtract the number of deaths, fertility, mortality, and then add the number of people who moved to that area within the year, in migrants or immigrants, and subtract the people who left, immigrants or out migrants, okay? So that's pretty much the demographic equation. Then with this basic information here, we try to do projections to the future. For example, if I know the size of the American population for several years, I have the PT here for several years ago, and I also know the number of births and deaths that happened in previous years. I can look at historical data. And I can also look at information about migration, both immigration and immigration. And based on this historical information, these historical trends, I can try to see how the population is going to be in the future. Nowadays, the levels of fertility and mortality are kind of stable. They are really low and stable. Fertility, you usually have, on average, around 2 children per woman in several countries. Mortality rates also kind of stable over time. They decline a lot and are stable. With now the coronavirus pandemic, it's actually increasing specific age groups. Usually older age groups are more susceptible to die because of coronavirus. So that will affect some of the projections from the new projections might do for these next years. But immigration and immigration, they vary much more. So population projections, trying to see how the population is going to be in the future, even if we have historical information about immigration and immigration, is hard because it varies a lot, right? If we have an economic crisis like we had in 2008 and like we are having right now because of the pandemic, then you have less job availability, less immigrants come to the US from other countries, right? If we have a specific policy that tries to avoid immigrants to come to a specific country, that might also affect the number of immigrants entering the country. Some other policies might try to do it, but we have a different effect. That's what we're going to discuss in the international migration chapter, that some of the policies at the end of the 80s that really are similar to the same policies that this previous president was trying to implement, increase border security, actually had the opposite effect. They were trying to decrease the number of immigrants, but increasing border security just made people, when they enter, they don't leave anymore. And they enter with their whole family instead of coming by themselves. So you had exactly the opposite effect of the policy that you wanted, which shows in that case that that policy doesn't work. So you should not spend tax money with policies that don't work. So it's a basic information that we know about it since the policies that were implemented in the US in the 80s. If we are concerned with science and data, that's what we would see, that that kind of policy doesn't work. And we're going to discuss that more in detail on the chapter about international migration. But this is just to show that the levels of immigration and immigration, they vary much more over time. And because of that, it's hard to do population projections for countries that receive a lot of people from other countries and that also lose a lot of people to other countries. Right? So that's why population projections can get difficult to be done. And just exploring a little bit this equation, if we have, and here, ignoring migration. In this case here, let's just look at the two components about fertility and mortality, the number of births and the number of deaths. If the overall number of births in a specific time period is greater than the number of deaths, we have a natural increase. So this term, natural increase, you're pretty much saying that you have more births than deaths in a specific society in a specific year. And I'm not taking into account migration. When I say that there is natural increase, I'm just considering fertility and mortality. I can have natural increase, but maybe so many people are getting out of that country that actually population size can decline, right? But when we use this term, natural increase, it's just a comparison between births and deaths in a specific society, in a specific year. Natural decrease is the opposite, when the number of births is smaller than the number of deaths in a specific society, in a specific year. Some people also use this term here, negative natural increase. I just think it's easy instead of using pretty much like using double negative here, you just use natural decrease. It means that the number of births in a specific society, in a specific year, was smaller than the number of deaths in that same place at the same time, okay? So those are terms that you're gonna hear a lot in demography, that you're gonna read in the textbook. So natural increase or natural decrease are some of them, as well as those concepts that I showed to you before. Immigration, in-migration, emigration, and out-migration. Right? All of these people are migrants. And when we take into account just the migration components of the equation, we can subtract immigrants minus immigrants. This is the term that we usually use for this. It's net migration. When we are talking about, we are just getting how many people got into the US from other countries and how many people left the US to other countries. In that case, I'm getting immigration minus immigration. That's net international migration. If I'm looking at Texas, and even in Texas, I could say like, I want to know how many people are moving from other countries to Texas and from Texas to other countries. That's also an analysis of net international migration in Texas, right? But if I'm in Texas and I want to know how many people move to Texas from other areas in the US and how many people left Texas to other areas in the US, I'm talking about net internal migration, which is pretty much what I just described, in migrants minus out migrants, okay? And when the number of people entering a specific area is lower than the people leaving that specific area, we have a negative net international migration or a negative net internal migration. Those are usually, so those are countries that receive less people than they send to other countries. So they are more sending countries because they have more people getting out of that specific country, going to other countries instead of receiving. And if we are talking about migration between countries, that's negative net international migration. And these countries could be described as sending countries. The US, for example, is the US a sending country or not? The US is not a sending country because the US receives more immigrants from other countries than people getting out of the US and going to other countries. So the US is a positive net international migration. The US is a receiving country. And if I'm just talking about internal migration, the terms like I'm saying here, negative net internal migration, positive. And for example, nowadays, rural areas in the US, they are net out migration areas. They have negative net internal migration. People living in rural areas, usually have more people getting out of those places than moving into those places. Urban areas, and that's not just the US, that's usually a pattern across all the world. Urban areas, they receive more people within a specific country than people moving out from those areas to rural areas. So they have positive net internal migration, and so these areas have net in migration, right? So those are just some examples. Sending countries, for example, I would say several, like Central America, Guatemala, Honduras, and El Salvador. They are more sending countries, really clear, sending more people to other countries than receiving. Net out migration, usually rural areas are, in this case here, receiving countries in terms of international. The US, and net in migration, usually urban areas have that. In Texas, for example, the whole state of Texas has been receiving many more internal migration migrants from the US than losing population to other states, okay? So with a simple equation, as we saw before, with information about number of births, deaths, immigrants and immigrants can also be internal migrants, we can have a better understanding of the trends of the population in those places. And here it's another set of slides that I added that are not in the textbook. It's just important for us to understand these terms. That's something that's taken it for granted, or that we expect people to know when they are reading the textbook or the content for this class, which is understanding what variables and observations are. What are variables? What are observations? Variables are characteristics that can change values from case to case. So just imagine that I have a questionnaire. In that questionnaire, I ask the person, what's your sex? What's your age? What's your income? What's your political party affiliation, for example? Those are questions in my survey, my questionnaire. And then the person will answer the gender, the age, the income, and the political party affiliation. So those are the characteristics of that specific person. So variables are characteristics of those specific, in my case, my example here, people that I answer my survey. But I could also look for, just thinking about the previous equation. How many births were observed in the US? How many deaths? How many people moving into the US? And how people moving out from the US in 2020? So these are the characteristics of the US in terms of births, deaths, immigrants, and immigrants. In this case, my unit of analysis, my case, is the country. I could get that for every other country in the world. I could get that for Canada. I could get that for Mexico, for example. Right? So variables are characteristics that can change from case to case. And these cases are my observations. They refer to the entity from which data are collected. They're also known as the unit of analysis, right? So when I have a questionnaire and I implement that questionnaire for each specific person, people, each one of these individuals are my unit of analysis. But let's say that I go to this household here that has these 3 people, and I just ask them, what's the average earnings? How many rooms you have in your household? In that case, I'm getting characteristics, variables for the household, not the individuals, right? So the cases, the unit of analysis, not necessarily is the individual. It can be households. And in my previous example about number of births, deaths, immigrants, and immigrants, I can get that information for different countries. So countries can be my unit of analysis as well, okay? Or states, or counties, or cities. So, but that's how we start building information. We start collecting data. And once, so here I'm just gonna go through explaining each one of them a little more. So variable is a characteristic whose value varies from case to case, from each one of my unit of analysis. Can be similar to different cases, but can also be, it can vary. And the idea is that those characteristics, we can measure them. We can quantify them. And usually these terms, we hear a lot these terms in social sciences. The dependent variable and the independent variable. The dependent variable is a variable whose variation depends on another variable. So that's the result of, I have some other characteristics that make me have this characteristic on this specific variable. Independent variables is a variable whose variation produces variation on another variable. So the independent variable is the cause of variation in the dependent variable. Let's think, for example, income. Let's say that income is a dependent variable. Makes sense to think that income is a dependent variable because income is a variable whose variation depends on actually several other variables, which could be some independent variables that affect income in this example. You have an idea? Sex, for example, we know that in the US, on average, even controlling for occupation, education, and everything else, women receive less money earnings than men, right? So sex is one independent variable. We know that people who live in urban areas have higher earnings, maybe because of the cost of living and better job opportunities and so on. Urban, rural, place of residence. Education. Usually people who have a college degree have higher earnings than people with lower education. Race ethnicity. We have a lot of variation in the US in terms of income by race ethnicity. So sex, place of residence, education, race ethnicity, marital status. Usually married people have higher earnings than other people in other marital status. So all these variables here are characteristics of those specific people, and they cause variations on income, which is our dependent variable. And sometimes it's not really clear what's the cause and what's the consequence, which variable is a dependent variable and the independent variable. In some cases, you might have reverse causality or endogeneity. What does it mean? For example, when we say that immigrants that enter a specific country, they might compete for jobs with other people in the US, and then earnings of the whole population can go lower. There are several studies that show that's not true, but let's say that the competition of having more immigrants make the earnings go lower. So that's immigration as an independent variable causing variations on income. But countries that have on average higher income, like the US, attract more immigrants. So in that case, income is the independent variable and migration is the dependent variable. So in that case, we have a really clear process of reverse causality. Right? But we usually hear a lot these terms, dependent variable, independent variable, to talk about which variables are the causes, the independent variables that cause variations in the dependent variable. But sometimes it's not really clear. Okay? Fertility and education. You could say that women who have higher education usually have fewer children. But women who are raised in a household with mothers with already fewer children, their parents will invest much more in the education of those women. So it's the fertility of their mothers or in the household that is affecting their education because they want to invest in education of their children, right? So there is reverse causality there as well. So it's not so simple when we talk about dependent and independent variables, but here, for our purpose, the idea is that you have some variables that are the cause, independent variables, and some variables that are the consequence, the dependent variables, okay? And there are all these different specific subgroups or specific applied social sciences that use different terms. The terms of dependent variable, independent variable is really popular in econometrics and also in sociology and in demography as well. And but you could hear these different terms that mean the same thing. Explained variable, response variable, predicted variable, outcome, regression. And explanatory, control variable, predictor, covariate, and regressor. So these are all synonyms. They mean the same thing as independent variables, and here they mean the same thing as dependent variables. And when we are doing any analysis, and that's not just in the case of social science, can be in any science that we have here, our theories and hypotheses are often stated exactly in terms of the relationship between variables, between independent and dependent variables. Once again, the independent variables are the causes, and the dependent variables are the consequence, the effects, the results of variation from the independent variables. Okay? And observations are collected information used to test hypotheses. So these are our unit of analysis, as I mentioned in the previous slide. And as scientists, we have to decide how variables will be measured and how the cases will be selected and tested. Who exactly is going to answer our questionnaire? I have a population that's too big, would be too expensive, so I can randomly select specific people, so I have to decide the method of selection, and I also have to decide which questions I will ask, right? And I have to decide if I'm going to ask questions related to each one of the individuals, about the household. The decision is based on my research question, on whatever research question that I'm trying to answer. You have a question? No.
My ears itchy, I'm sorry.
And observations, the idea is that we can measure social reality. And in this case here, we have a lot of qualitative analysis that we can do, focus groups, in-depth interviews, ethnographic research. But in this case here, we are talking about variables for specific cases, for specific observations that can be measured with numerical data. That's what we usually do in demography. That's what we usually do in population studies. Information can be organized. All this information that we collect from these observations, from these cases, the characteristics of each one of these observations can be organized in databases. The variables, they appear on the columns of the database, and the observations, they appear on the rows, right? So this is one example of a database. We here have 526 workers. We have 526 rows. With 5, 6, 7, all they are here until 526. So each one of these rows here is one individual from which we collected information about that specific individual. And we ask information, what's your salary per hour? We put it here from that individual. And I was asking the questionnaire, ask how many years of schooling do you have? Years of experience in the labor market? What's your sex, female or male in this case? And what's your marital status? In this example here, simplifying either married or not married, right? And putting married is 1 and everybody else is 0. Here, female is 1 and everybody else is 0. So I'm pretty much doing exactly this. I'm collecting data in a numerical format, okay? Let me just show you here on Excel, for example. This is how we can, all these election polls that we heard so much in these last months, for example, we have a specific individual, so I asked this question for 1, 2, 3 people. And in the questionnaire, I asked, what's the age of that person, education, and which candidate they would vote. The first one was 20 years old, and education here, let's measure education in years of okay, let's just do, in this case, let's just do high school. I'm not going to put in numerical format here. And the candidate, they voted to candidate A, okay? The second one is 55. It has college and voted to candidate B. And this one is 60. It has college as well, and it voted to candidate A. So when those different agencies, they do these polls, election polls, they have this data organized like that. You have the columns for the variables and the rows for the observations, each person who answered your questionnaire. This is the micro data. This is one example of micro data. You have information about all the people who answered your questionnaire. And in this other example here, this was also a micro data from the slides. But what we usually see from when we have the results of a poll, we have here candidate B, and we have people with high school and people with college degree. What we get, how many people with high school voted to candidate A here? One person, and to candidate B, nobody. For A, nobody voted for A who had a college degree. Sorry, one person, and here, one person. Okay? So here, pretty much we have like one in total. We have two people here, and then we can do in percentage terms. High school, college, just get this one, divided by this, just doing a really simple case of how we organize microdata in the table format. So in this case here, I'm just getting these people here divided by this one, multiplied by 100, so I know how many people with high school voted to candidate A. 100% of the people in my sample with high school voted to candidate A. And what about college? 50% voted to candidate A and 50% voted to candidate B. So what we usually see in the news or is this table here, right? We say that like in this example, 100% of people with high school voted to candidate A, 50% of people with college voted to candidate A, and 50% voted to candidate B. But in order to get into this aggregated table, they had to have the microdata. So those are also important terms. Microdata, that's what's highlighted here right now, this part here. The aggregated data is this part here, okay? And of course, here as well, if we just sum, we have 100% in both of them, okay? Both of the columns here. So this is really simple to understand. It's pretty much, we have the characteristics of those people in the columns. Each row is an observation, is a case. We have the microdata, and we can get this microdata and organize it in tables in the aggregated format. A lot of websites that I'm going to show to you here throughout the semester, and even for your purpose, even for your papers in different classes that you might take, and if you are doing any kind of data analysis, you can already get really refined, really good data for your analysis that's already aggregated. You not necessarily need to have microdata to do a good analysis. A lot of the websites that I'm going to show to you, they have data already aggregated, and that can give you really refined information to answer your specific research question. All right, so all these terms are important to understand. Variables, independent variables, dependent variables, observations, unit of analysis, which is the same thing as observations and cases, microdata, and aggregated data, okay? These are really important things to understand when you're talking about data analysis. Any questions? So now I have a series of our slides here to just give you an idea about what's going on in terms of the coronavirus pandemic. Everybody here, of course, has been reading and hearing about it all the time. My idea here is to show you, in order to understand what's going on, we have to collect this data from all these different sources. So one website that usually update information daily or more than once per day is this Worldometer. And they have information about the total number of cases, deaths, total number of people recovered, and so on for all different countries in the world. So this case here is also a database. This database here, for each one of these columns, we have the variables, which are characteristics of each one of these countries. And the observations, the cases in the rows, are my unit of analysis. My unit of analysis in this case here are countries, right? So my unit of analysis in this case is our countries, and then we have the characteristics of these countries related to the coronavirus pandemic. And this is data from the beginning of the last semester, fall 2020, when I was teaching this class last semester. We had around 180,000 people dying because of the coronavirus in the US and 115,000 in Brazil and so on. And this database here is organized, is ordered, is ranked by the total number of deaths. So you can, in this website, you can just click on the column that you want to sort it. And I sort it by the total number of deaths. You could also do it by the total number of cases as well if you wanted. And here we have the total number of people who recovered, active cases, serial critical. And we also have the size of the population in each one of these countries. So if we have the number of cases and divide by the size of the population and multiply by 1 million, we have the total cases by 1 million people. If we get the total number of deaths divided by the population and multiply by 1 million, we have the number of deaths by 1 million people in that specific country. Okay? Total tests, and this number here divided by this, multiplied by 1 million, we have around 232,000 tests per 1 million people in the US. And in this case, tests, we have to remember that the same person can take the test more than once, okay? But this was at the beginning of the last semester when I was teaching this class, 181, and now we are above 400,000, and in Brazil above 200,000, okay? And because the population didn't vary as much within one semester to the other, the rates really increased a lot. The previous slide, 547, 1231, in Brazil, 543, 986, okay? So these are major data about the coronavirus pandemic for each one of these countries. And I'm showing here just the top 20 countries with the highest number of deaths for each one of these dates. Here, there were the countries with highest numbers of deaths up to the 20th country in August 24. And January 19th was last Tuesday, the first day of this course. And then I'm just going to get here to the countries, the 5 countries with more deaths: US, Brazil, India, Mexico, and the UK. And then I go into this other website, Our World in Data. You can just type this in your browser, you can get there, and you can make your own graphs, you can select your own countries. And all these links are also in the course website. And these are cases all for January 19th, the same last Tuesday. And there are different graphs that you can do from this website here. Here I'm starting with a really simple one. The number of new confirmed COVID-19 cases, and that's linear, just the total number of cases that we observe. And because there is so much problems with reporting, so much variation per day, that usually all these different data sets or websites that are showing information about the coronavirus pandemic, they show in a 7-day average. So the information for a specific day, you get the number of deaths, the number of cases in this case that were reported in that day, and you get the previous 6 and get an average and report it here. For this day, you get the number of cases reported in that day, get the previous 6, and take the average out of these 7 days, okay? So it's just because you have so much variation, and so you want to just smooth the curve. In the overall number of cases, much higher in the US than in Brazil, UK, Mexico, and India. But of course, you would say, you have to take into account the size of the population of each one of these countries to see how you have to pretty much calculate this column here, cases by the size of the population. And this website also allows you to do that. And that's the next slide, new cases per population. So even getting the new cases confirmed each day, but in this 7-day average, divided by the population of that specific country, you still have rates really high in the US, lower only than the UK. In the UK, in these last days, it actually passed the US really bad, and it's starting to decline a little bit. Because the population in India is so big that the rates are really low compared to these other countries, and Brazil in between, and Mexico lower than Brazil. Okay, but then you see all these variations. The US, the pandemic was really low at the beginning of last year, and then you start to see the first wave, and you saw it again around the summer, and then you start to see all this increase in the US here in red, exactly when you start to have Thanksgiving and Christmas and so on start to increase again, okay? The same website, now number of deaths, and showing again the US in red here, really high number of deaths back in April, and then increasing again in the summer, and then increasing again around Thanksgiving and Christmas. And this graph here of deaths is really related to the graph of cases. When cases increase, in the previous one here, a couple of days later, a couple of weeks later, you see increases in deaths for all these different waves. That's what you see over here, okay? And if you just put these graphs in the top of each other, as another slide I'm gonna do it, you see that really clear. But number of deaths, it's overall the absolute number. It's also important to calculate the rate divided by the population. Why is it called the rate? Because the denominator are the population. The population has the risk of dying of coronavirus. The population denominator has the chance of going to the numerator, of dying for the coronavirus pandemic. So that's the rate. And that's what we see here. The rate of deaths per population, and get information since February through January 19th, higher in the UK, and then US, Mexico, Brazil, and India. You saw that the rates of cases in Brazil is higher than Mexico, but in terms of death, the death rates are higher in Mexico than Brazil. And you can do these graphs here for several other countries. You can go to the same website and select several other countries. You can select only the US. You can do all different sorts of analysis, right? Another interesting term to learn during this pandemic that we have been hearing a lot since the beginning is a term about flattening the curve. Our objective as policy makers is to implement policies that will control the pandemic so the cases don't increase as much. We have to flatten the curve. When you look at the number of cases here, linear, it's a little hard to see and understand this concept of flattening the curve. So if you just pretty much get the number of cases, the original one, the number of cases in each one of these days here for a specific country, and you just take the logarithm of that variable. So this is the case of the US. The US, these are the cases, really easy to understand. This year here, these are the number of cases that were reported this day here. These are the number of cases that were reported that day. I get the previous 6 days and take the 7-day average. That's what is explained here. And then if I just take this one here and take the log of this curve, that's what we have here. This is only the US, just to explain you this concept of flattening the curve. What we want is that the number of cases were increasing a lot at the beginning, and then afterwards you start to control it. But the problem is that it increased again around the summer, and then it starts to increase again around Thanksgiving, Christmas, and the winter break, right? So the pandemic is not still controlled in the US. Why, when you take the log, we have this different shape of the curve? The curve was really exponential, increasing a lot. And now it has more this, it increased at the beginning, but then afterwards stops. Because the log, when you take the log of a specific number, the numbers that are much higher than the others, they get more compressed. And that's what the analysis that we want to do as policymakers. I know that this is a huge issue. These are still high numbers here of people contracting the virus. But if we can at least control here a little bit the number of people contracting in a log scale, we are saying that our policies are working. But that's not what's the case here. But you cannot just look at the data in the log format. It's also important to look at the linear graph as we saw before. Right? It's just to show you, to understand the pandemic that's going on. That's one problem that we have, that I'm giving as an example. You have to get all different kinds of data. Another kind of data that's available in the same website, our world in data, the same one as the previous graphs, is the positivity rate of tests, the share of daily tests that are positive in the US, also shown in a 7-day average and in percentage terms. It increased March, April, and then last summer, and it's increasing again the number of tests that come out as positive. And in this case, I selected only in the US just to show you that we can have this information as well. But we could also have this information from other countries. If you go to the website, you can select the other countries as well. And here, the New York Times is also compiling this information about the pandemic. And here's exactly what I told you to you guys before. I'm showing here the new reported cases by day. They also reported as a 7-day average, the same way as our world in data does. And here the number of deaths. And you had an increase here, a little like in early April, and then a little bit more 2 weeks later in April, you have the increase in deaths. Here, end of July, you have an increase of cases. Around 2 weeks later, at the beginning of August, you have the increase in deaths. My class finished in the last semester in November, and everybody here as well, like towards the end of November. And that's when we had, again, the increasing number of cases. And some people are arguing, oh no, but the cases now are increasing, but they're increasing more among young people who are not so susceptible to die. But then what do we see? A couple of weeks later, the deaths increasing even more and being higher than what it was back in April and May, right? So the pandemic is still here. But you say, well, but people are saying that like more than 4,000 people are dying in the US per day right now, more than it was, for example, 9/11 here per day. And here you're showing that's below 4,000. like somewhere around 3,000, because this curve here, again, is the 7-day average. We get information of deaths of that day, and we get the previous 6 days and get the average just to smooth the curve. The original data is this light gray columns that we see here in the back. And then you see that in specific days, you did reach more than 4,000 reporting deaths in the US per day because of the pandemic. But even the average, it's already above 3,000, right? So all this data, already aggregated data, all available in these different data sets, these different websites, and each one of them, they help us better understand what's going on. In previous times, when I showed this graph here, I would put just a line here showing where this peak was, and then right after that was the peak of this one here. But I just thought it was like getting too confused. But you exactly see that when it gets into this peak of cases, 2 weeks later, you get the peak of deaths. And that's what we are seeing happening right now. And here in Brazos County, I think ICU beds, they are like around 130% of capacity being used. So you had a specific number of ICU beds in the county, and they had to just create some more because of cases that are really severe and need people in the ICU beds. So that's a huge problem in the country as a whole. This is the number of hospitalization, because you could say, oh no, the number of cases might be that high, but it's not so severe. It is because the number of deaths is increasing. And also the number of hospitalizations is increasing, right? So this is pretty much the COVID patients in hospitals that specific day, also 7-day average. And that's for the whole US, data from last Tuesday. If you go to the New York Times website now, you're gonna have information more updated for these last 2 days. The New York Times website too, they show the data for each one of the counties in the US, so you have this information in space. And I told you on Tuesday that in demography, we try to understand fertility, mortality, and migration. In this case, we are talking about mortality or morbidity. Morbidity is the incidence of a disease. So cases is morbidity, deaths, mortality. And I also said in the previous class that we want to understand the distribution of the population. In this case here, the distribution of cases of people infected by coronavirus. And this is information that I got not exactly at the beginning of the last semester, but in October 21st, when I got information that's more comparable to the maps that they have now. And these are average daily cases per 100,000 people in the past week. So these are more new cases in this past week in each one of these counties. Counties that are darker, more reddish, they have higher rate of cases per population. And then at the end of last semester, November 23rd, you see a spread throughout the country. So in the middle of the country, you start to see much higher incidence of cases. And these are rates, cases divided by the population of these counties multiplied by 100,000. That's what's explained here. And then from last Tuesday. So that's really interesting to see these three graphs. Here, concentrated more in East US, and then spread more towards the West and more in middle of the US. And now you see again in more, California, Arizona, Texas as well, and in the East Coast as well. A really high rate of cases. And here, cases divided by the population multiplied by 100,000. And for Texas, the New York Times has information for each one of these states in the US. So I got this data for Texas specifically. And that's the same way that was shown for the US as a whole, cases and deaths. And you see when the cases increase, a few weeks later, deaths, and then the same thing here towards the end of the year, Thanksgiving, Christmas, cases increasing, and now deaths increasing. And the raw number here in a specific day in January reaching above 400 deaths in a specific day in Texas. And also, the New York Times has information. Kind of pretty much do a zoom in that map, and for each one of the counties in Texas. And this is data from October 21st, like towards the beginning of the last semester. And you see that was not still spread out. Brazos County here. And then you start to see November 23rd, towards the end of the semester. And then more recent data. It changes a little bit. It was more towards the west, the highest rates of cases, and now back to the south and more northeast of Texas. Okay? And also in the Houston area as well. And this is another interesting kind of data available in the New York Times. Colleges with coronavirus cases since the pandemic began. That's going to be a really interesting case to look at throughout this semester. October 21st, 1,661 cases at A&M. It was only lower here than Texas Tech in Texas. And then the same November 23rd, 1,600, 2,500. Break. Students go home. Doesn't increase as much, 2,700. Throughout the semester, 16, 25. During the break, only 25 to 27. So it's going to be really interesting to see throughout the end of this semester how we're going to get there, comparing these four numbers within the semester, and then the break, and then the semester again, right? So this is to show you all this data that I compiled here. They come from different sources: Worldometer, Our World in Data, the New York Times. I show data for several countries. I show data for the US specifically to explain specific concepts such as flattening the curve. And then I showed you variation in the US by counties. And then Texas, and you can have those same kind of graphs and maps for all different states in the US. But so that's how you try to understand what's going on. You have to collect this data from different sources. And I don't have the micro data. I have only the aggregated data already given to us or organized, but writing about this already could be a term paper for a class, for example, dealing with this topic, right? All data available for free. I don't know, the New York Times, I have the subscription, but I think you can still read 10 articles per month, as far as I know, but for free. But it's just to show how when you're trying to understand a specific social problem, you have to go to different sources, understand different aspects of that problem to have a better view of it, right? And the number of cases are increasing because the number of tests are increasing. That's wrong, you know? So you should just read at this, the positivity rate here from this graph. The number of tests divided, the number of positive tests in the US divided by the overall number of tests, it's increasing. So it's not because you have more tests, you have more positive cases. In this case here, again, the test that became positive divided by the total number of tests. That's a rate. That argument, easy to be, to say that's not based in science. It's based on possible beliefs, wishful thinking, or whatever. But data is not showing that. Positive tests divided by total tests, rate. That's what we have to analyze. The cases are increasing now because more people younger people are getting it, not going to die. Oh, what is this here? Higher levels of death than it was at the beginning, right? So that's not true. Data. That's why we are here, science, right? So that's what the argument is all here. It depends if you want to understand the reality based on science or based on whatever belief you have, right? Hospitalization rates, hospitalization of people because of COVID, those are severe cases, people that could die. If you look at the data from the Brazos County Health, the health department, I follow them on Twitter, and then I think it was like around 130% the occupation of ICU beds, 130% or more at this point. Okay? So just to show that data analysis is tough because you have to go to different sources, but that's how you understand the issue. It's not just based on discourse. In demography, we have, depending on the kind of study that you have, you can classify it in different ways. So when usually I'm just talking about variables, demographic variables, explaining other demographic variables, that's usually called formal demography. When I'm trying to understand the association of demographic variables with sociological variables, psychological variables, political variables, all these other variables, I have what's called social demography, or in this case here from the book, Population Studies 1 and Population Studies 2. When we are just interested on associations between demographic variables with other demographic variables, we are pretty much doing formal demography. Some people would call this a peer demography studies. In our case, in this class, we're going to be doing more social demography, which is the association of demographic variables with variables in other areas of social science. Okay? Some examples for better understanding. Formal demography, the independent variable or the independent variables and the dependent variable are all demographic. An example here. For example, if I look at the age composition of a specific population, if a specific population has a higher proportion of children in that population than people in reproductive ages, than people above 15 years of age. This is a population that's younger, have a higher proportion of children, so that will affect the birth rate. Birth rate will be lower. If I have more people between 15 and 49 years of age in reproductive ages, proportionally, age composition a little older, then birth rate will increase. In this case here, these two variables, age composition and birth rate, are demographic variables. But it could also say that in this example here, there is a really clear reverse causality, which is something that I mentioned earlier today. I just said, if we have more people in reproductive ages, you increase the birth rate. But if we have a high birth rate in specific year in a specific population, what's going to happen? We're going to have more children, and then the age composition of that population will become younger because we have a higher proportion of children in that population because we have more children being born. Birth rate increases, we have a younger age composition. In this case, I'm talking about two things. Formal demography, a demographic variable associated with another demographic variable, and I'm talking about reverse causality. Age composition affects birth rate affects age composition. Sex composition of immigrants to a city. What's the percentage of women moving from other states to Texas or from other states to College Station? The percentage of women, out of all people moving to College Station from other places in the US? What's the proportion of women? What's the proportion of men? That composition will affect the sex ratio of the total population in College Station. What's the sex ratio? The number of men divided by the number of women. So if we have more women moving to a specific city in a specific year, that will affect the sex composition of that whole city. These two variables here are demographic variables. So it's 4:30 right now, but here pretty much population studies, it's when we have a non-demographic variable explaining a demographic. It's also known as social demography, which is the topic of this course. And in this case here, demographic explaining non-demographic. So I will go back to these two slides before we go further on Tuesday. And on Tuesday, by the end of the class, we're going to have the first quiz. It will be open on Canvas at the end of the class at 4:30 on Tuesday, and it's going to keep opening Canvas until noon of Wednesday. But I will remind you about that, okay? Thank you very much, and I see you guys on Tuesday. Have a great weekend. Thank you.